Thank you, Kali, for this nice introduction. And first of all, congrats to PyData with 10 years of this awesome conference. I'm really happy to be here. As Kali said, my name is Judith Dijk, and I want to tell you something about image processing, artificial intelligence, and autonomous systems. And I give you a bit of my background so that you understand why I'm telling you this. As Kali said, I did my master's and my PhD at Delft University of Technology in applied physics, mainly imaging, image processing, how to get information out of images. After that, I worked 20 years at TNO as a research scientist. And the last year, I worked at EDA, the European Defence Agency, as project officer. And I also want to mention that while I was at TNO, I was a liaison at the Maritime Warfare Center, the Dutch Maritime Warfare Center, which was really interesting for me because my colleagues at TNO and at university are real scientists, so they want to have the best solution that they can make, the less noise, the best whatever. And then if you get to the operational people who have to use it in the field, they have all these other requirements. They say, maybe I don't want to have the least noise, but I want to have it always working, or never have a bad answer or something like that. I come back to that later in the presentation, but please notice that there's a difference in the best thing you can make and the thing that people really want to use. And I wanted to show this with two applications. The one is on situational awareness, what is happening around me, and can I see if someone is a threat for me? Remember, I'm from the defense sector. And also autonomous systems. What do we want to develop for autonomous systems, and where is this going to help? But first start with situational awareness. I made a lot of images here with generative AI. This one also, I asked it to give me a harbor full of ships, and I got the small ships. But imagine you have a harbor, you are maybe not sure if everyone is friendly towards you. Can you see what's happening around you? That's the main question here. And why is this important? Well, the main example people use for this is the attack on the USS Cole in 2000, I think. Yeah, in 2000. And in this case, there was an American ship, the USS Cole, in an harbor of another country. And in the middle of the night, I think, two small ships drove up to the hull of this ship and exploded. And I think 5 people died, which was tragic. But also people realized that they didn't see it coming. The ships, they only saw the small ships when they exploded and when the damage was already done. So can you see what's happening around you? Another example is in images you maybe can see if there's aggression. And we as persons are really good in seeing if someone is aggressive. But the question is, can you also see that using camera images, and can you learn what aggression is? And again, it seems really easy, because when someone's doing something like this, then he's probably angry, or maybe he just parties because his favorite football club just has won, which is also something like this. And here again, I have an example from the Netherlands. A couple of years ago, I forgot all the years, in 2009 there was a party on the beach in Hoek van Holland, which was a free party. A lot of people went there with small kids, with families and all other people. And it really escalated, and in the end the police, I think, shot one person. So the escalation was there, which was really tragic. But what I found also interesting here was that the people who were there, they felt that it was going wrong. And not just before everything escalated, but 2-3 hours before, the families with the small kids went home because they said it didn't feel right. The atmosphere was not okay. I found it really interesting. What is not okay in this kind of thing? So I asked a lot of people I worked with, what can you see? And what they said is you can see that the groups are different, so people are too close to each other, people are forming small subgroups in a large group, and that, in many occasions, results in escalating events afterwards. And one thing which was closer, but was also really interesting for me, you can also see if men start to fight. I didn't put on a pants, but if men start to fight, they start often with pulling up their pants before they do so. So if you see that, So for me, the interesting thing is, can we get this information out of the images? I call this information extraction. You start with images. I remove the part when we acquire them, so we have this image, and can we find actionable information that you can use? And in my field, you have two kind of information that you can get from it for defense, which is based on objects. Can I find objects? Can I detect them? Can I see what it is? Is it a ship? Is it a motorboat? Is it something else? Can I identify them? Because you can say, well, maybe this is the Fisher ship from Mr. Janssen or something like that. So the specific ship, or in persons that you should know, I'm a woman, that's a classification, but I'm also Judith Dijk, which is my name, so that's an identification. You can see, you can track objects over time, so can you see where they're going? And can you also see that there's possibly a threat? Remember the small ships are going towards the USS Cole? Well, if you would have seen them, you would like to have them detected as a threat. And you can also look at situations. So what's happening around me? Is everything okay? For instance, here I see you all sitting. Some people are walking, but not so much, fortunately. Can I see if there might be a threat or some situation that I want to have or not have? Can I predict what the future will be in 1 minute, 1 hour, 1 day maybe? And also, can I see if there's an anomaly? And those things are really hard, because if you want to find an anomaly, you also need to know what the normal situation is. An example here, I didn't get a picture from that, is, for instance, in Afghanistan, in war zones, if there are no children on the street, there might be an attack. Because if there are children playing on the streets, and their parents know that something is coming, they will get them inside. So having laundry outside, having children at normal times on the street, and changes to that are also really, really important. The second part I want to talk about is about unmanned systems. Again, a nice picture by generative AI of the spot robot. I asked him to make a spot robot for me, and he actually did it, so that's really nice. But of course, you have a lot of other unmanned systems as well. These were military unmanned systems, so a drone, a large vehicle, and a small vehicle. And the point that I want to stress to you is unmanned is not autonomous. Often there is really one or even more people directing the drones, directing these unmanned systems to what they need to do. So if you say the military saves people, in Afghanistan, which is already 10 years ago or 10 plus years ago, they had one drone which was operated, and they needed 15 people to operate it during the day for 1 hour. So that's not much less, or maybe even much more than just having a pilot in the air. So what we want to do to make things autonomous is to add a brain to the system. Can we make it self-aware? Can we know what it does, what it needs to do, and how it needs to do it? I come back to that later, but please remember this image. I really like that. So you have this robot, and you want to give him some consciousness, which again isn't easy. And then the promise is that it will be more efficient and more effective. But how do we get there? I come back to that later, but I first want to show you why we want to do this. At TNO, we worked a lot on the search and rescue case. So here we had this TNO robot at a mock-up image at our premises. And he has to go in, and he has to find persons and hazardous situations. Which, again, is not so easy, because person finding is more or less okay, but you have to look into all the rooms to find the persons, and maybe also to do some triage. Which people need to be used? Is it a child? Is it a grown-up? Is he really in need of help, or can he just walk out himself, or something like that? And hazardous situations is also something, maybe you can define it, but it's hard. But you want to do this, especially in cases where you don't exactly know if the people are there, or where you don't have enough persons to do something. For instance, like with the earthquake in Turkey, if you could have autonomous systems, so not directed by persons, but really autonomous systems who could help you find potential persons in rooms or buildings you cannot enter or you don't know if someone is there. It would really, really help. So that's one use case. And the other one is drones, as used in different wars. So for instance, in the Ukraine-Russia war, we really see the war changing, shifting towards drones, the use of drones. And but please note that most of these still are remotely piloted. So there are lots of Ukrainians and Russians, I guess, somewhere behind the war zone, directing all these drones towards their targets. They use a lot of drones with munition, so that they fly towards some target and then they explode. And they also have these kind of small ships which can autonomously go somewhere and explode again, like in the USS Cole case. And I didn't do it now, but I did it a year ago or so. If you look into the internet, you can find a lot of information about these drones, how they're used, and also how it's evolved over time. For instance, on communication, and what does it mean if you have a drone and people find where you're directing it from. Have a look at the task, similar to the image processing. There are, at least in my opinion, 4 different tasks. So you want to have a system navigate. Can I go somewhere? Which sounds really easy again. But if you are in the open world, so where you don't know what it is, you might encounter, like here, a mud pool. Question is, can you go through that? I don't know. But if you really want to know that you don't get stuck, you have to go around. But then the question is, can you do that? Because then you might flip over. So navigating the world, as easy as we find it, also for a robot, is not so easy, and also not really only using Google Maps to get somewhere. The second question the robot has to ask, what's my situation? Where am I? What is happening around me? And that's really crucial. I will show an example later. Then you have to do planning. So what task do I want to do and how do we do that? And finally, you have to perform the task. And at some point, you also need to have self-awareness, situation awareness, and context awareness. So self-awareness is, what can I do? For instance, if you see the mud pool, and you see here 2 different autonomous systems, the one with the tracked wheels or the large wheels, can do different things in navigation than the spot robot. For instance, the spot robot can walk the stairs, and this other thing cannot. But the ski probably can go through the mud, and I don't advise you to do that with the spot robot. And here you also see a spot robot with a hand or a gripper there, so we can also manipulate things which the other one cannot do. So self-awareness, what can I do, what am I capable of doing, is really important. I already spoke about situation awareness, so what's happening around me, what do I want to am I happy with it or do I have to change something? And you have to be context aware. And then again, if I go back to the large people, the crowds of people, crowd control, imagine you are in a concert from heavy metal or a violin concert. In the first case, you would expect people to be much closer than in the second case. So if you put the same meshes on them, they will be wrong at some times. And then I want to talk to you about open world challenges. So the work that I did on autonomous system, I do on autonomous systems, is expecting you're in open world. So not in a factory where the robots always have the same task. For instance, a car factory, a car comes by, he puts in a knot, then comes back, puts in a knot. So that's always the same, but here we have an open world. And in the open world, things can change, things will change. And unexpected things, unexpected events will happen. I said can there, but it will. For instance, if you drive a car and you see a ball coming up the street, as a human, you just brake a little, because maybe there's a child coming past it. Now, these kind of things you can try to model it, but yeah, you probably cannot model everything that will happen. So you have to somehow be aware that something strange can happen. The context can change. I come back to that later. And the operational rules may conflict. And you have to interact with humans. In this case, I put a picture of my two sons here. Basically because I wanted to tell you something about the right one, Caspar, related to operational rules and context. Caspar is an autistic boy who was studying. He's studying now, but he was on a school with all autistic children, and I went to Berlin to a school trip, and he got a long list of rules with him. So in this trip, you have to oblige these rules. And one of the rules was, when in the hotel, don't step out of the window, which is really a great rule, I think. But I told him, Cas, please, if there is a fire and the window is your only escape, please climb out the window, because then the context changed. You have to evacuate, and the room is closed, or the door is not available. So then, this one trumps the other rule. And he said, Mom, of course I know. But he had in his class, he had this really strict autistic children who had a hard time thinking that the context changed, and then you have these one rules which are on paper, and the other one is really implicit. And we all know. I think if I ask you, step out of the window in case of fire, you would all do. But please know that we learned that, and we learned to find this context change. Another one, again, and I love to compare. I love my son, and he's a really nice guy. But I also love to compare autistic behavior with autonomous systems, because there are a lot of comparisons, but also some differences, of course. Another example, really Dutch, also from an autistic child who went to school by bike every day, and he kept coming late at some time. And then they found out why, because he encountered this sign over here, which says bicycles descend. So the boy really descended, and he walked to school. Because this sign exists, but there's never a sign which says, now you can start cycling again. You just have to know. Or in my case, you just start too early and disregard the sign. But if you really follow the signs, then there are some really direct signs like this one, but also the indirect ones where you say, well, if I'm past this large thing over here, I can just start biking again. And again, I would do that. If I go a little bit back to the image processing, where I started my career, I told you these kind of things you want to get out of images. And in this case, we did it really like these kind of tasks. So we can do a detection. And in this case, you have a bounding box around the cat. I tried to make some cat and dogs examples. You can do classification, so this is a cat. You can find the cat in the entire image over here. So the pixels inside are cat and the pixels outside are not. You can do activity recognition, so in this case the dog is running. I was looking for a threat. I wouldn't want to encounter this dog, so you can see this as a threat detection. And also some situation awareness. So can you see that this dog and this cat are cuddling together? And then I think in the first 15 years of my career, I did a lot of these things, which ends in these kind of results. So this is the harbor of Rotterdam, and here you want to see the boats in the harbor. For people who know Rotterdam, this is a small water taxi. I think this one as well. You see the large ships here in the back. And you can see that you get some information on which ships are there, where are they going, what is their speed, something like that. And you can even extend this with looking at how many people are on the ship, or maybe it's a bit strange behavior in this course or something like that. So this provides some information on where everything is. But then in 2014, things changed with respect to artificial intelligence. When I did my PhD around 2000, people were already working on neural nets, and there was a promise that it would do something, but the real promise came in 2014 in results. And looking a bit back, I listed 4 important AI developments. So it started in 1950 with a Turing test from Alan Turing, who says, if you communicate with a computer and you don't see it as a computer, then it's probably a good AI. In 1997, there was the famous match between Deep Blue, a computer, an AI computer, and Kasparov. But this AI computer was totally rule-based. So they put everything that could happen in the computer, and then he won, which is interesting, of course. But then they had, in 2016, the AlphaGo match between a computer again and the world champion in Go. And here again, the computer won. But what was interesting here is that the computer didn't know the rules. He learned them by reinforcement learning. So he tried to do matches against himself. And then when he won, then he knew that. And when he lost, he tried something different the next time. And by doing that, I think really many times, he eventually won from the world champion. So this was a really learned system. And for me, I'm not sure how you think about that, but ChatGPT coming out in 2020, I remember when it came out and I said, wow, that's just a language model. But it's really changing things in AI and also what you can do with it. And I want to go a little bit deeper into that now. So I see basically 4 classes. Maybe you see more, but I see 4 classes: logic, machine learning, deep learning, and generative AI. The logic part, I'm not sure we did it with image processing, but here you say, what do I know about the world? If I look at a cat, I think he has pointy ears, he has small, a T-shaped nose, whiskers, a tail, 2 eyes. You can have other things, and you can just check, does he has it, doesn't he have it? And then you can say, well, this object is a cat. So all these logic rules based on a model of the world. So what you need for this is a model of the world, and then the rules, of course. When I did my PhD in 2000, we were working on machine learning. So can we find features in the image, maybe density or curves of something looks like eyes or something like that? And can you then use the features and label data to find a model to discriminate all these classes? And famous examples from it are the k-nearest neighbor classifier, where you say, well, if I have this feature space, I put all the points in the feature space, then the one that is nearest to a labeled is probably the same things. And after that, also a support vector machine came, who really nicely distribute the features over the space and find the best discriminator. But here you need all these features. So you need features and you need a lot of labeled data to find the different classes. In 2014, with AlexNet, there was the first thing of deep learning. And here you have a deep learning model. I put it as a black box, because it is often a black box. You do put in a lot of examples over here, and then if you put a new non-label thing in, then it says, well, this is a dog. So what you need here is a lot of labels. And the last one, the generative AI, also a black box, maybe even blacker. I'm not sure about that, even more black. But then you use, again, a lot of data from the whole world. And then you just need a prompt. In this case, is there a dog in the image? And then he says, yes. Or you can ask, where is it? So if I summarize, for the logic, you need models and you need rules. For machine learning, you need features and labeled data. For deep learning, you need more labeled data, really lots of labeled data. And here for generative AI, you use every data and you need prompts. So, and I go back into detail in the last 2. But first, if I look at my work, there are some challenges. We have to go from data to information. Well, that's on the whole line, because if you just have the data, you have pixels and you cannot do anything with it except for look at it. But you also want to have actionable information. So I don't want to, if I need a result now, I don't want to wait for 3 hours or 2 days to get a result, because maybe then the event is already over. You want to go to on-edge computing, especially if you have a lot of small assets. For instance, in autonomous systems, you don't want to send every data sample to a centralized point, but you want to do it on edge, on the platform itself. And if you look back at machine learning, and maybe also deep learning, a lot of these models were really task-specific. So they had one really good speech model, one really good image model, but can you make models which you can ask something and then give you something back? So to start with deep learning, if I look at the challenges in the military domain, then you can say that application in the military domain is different than in civil domains. For instance, you use different kind of images, and you want to have target detection at a really large distance, which often results in not so many pixels. There's little training data, especially if you look at situation awareness of events. If you want to predict a terroristic event, I'm really glad we don't have so many terroristic events happened, but then you also don't have so many training data. So you have to do something with data. They really need trust. I talked to someone, for instance, in the harbor example, where you saw this small boat going to the image, to the video, and you detect it. I talked to someone who said, but if it doesn't detect it, and I see it as a human really good, I will never use it again, Judith. And that, why not? He said, I will never trust it, because I can see it, and I trust myself, and I know that if it's windy, or if it's foggy, or if it's night, I'm not able to see that well. I understand that. But if I have a crystal clear image, and the system doesn't detect it, I will not use it. And then we have the online adaptive systems. To provide an example here for the difference between military and civil domain, there are a lot of detectors for cars in the world. Also, you can find them online, and they do a really good job. But again, in the military part, oh, this one shouldn't be here. It should be there. But in the military part, you see here a tank in infrared, which is really harder to detect. So you somehow have to learn that as well. And one of the things to do that is to retrain with a different data set. So here, this one was trained on the MS COCO dataset, which is a standard dataset you can find online, with 80 classes of RGB images, with 80,000 images, and a neural net provided a nice bounding boxes around the ships, as I would like. At TNO, we recorded ourselves a dataset in the harbor. Oh, it's not here yet. So this one, you see here infrared, so this ship is really hot, because the more white, the more hot it is. But you see also that it doesn't resemble that one. But you can, if you have here 1,600 images, and compare that to the 80,000 there, you can retrain the system so that it detects it as well. So what you can do here is to use this model and do a little retraining, and then get a model which you can really use in the defense sector. I wanted to say something about the life cycle, because that's also important. In standard, traditional technology, you have something in a factory here, so design development, do integration, test and validation, and then you're fine. So you say, please use it. Here's your phone, it will work. In the defense part, you also do some training, evaluation, and update. So if you train and you see that's not working, maybe you want to update. But what does that mean for the validation and verification that the factory defined? That's hard. And even when you deploy it, you have different times. You can say, when I have mission time, I say, I'm going tomorrow to this location, so these are the targets I expect. Maybe do some update on that. Operation time is when you start, and runtime is when you are really in the middle of something. And at all these things, you might update the system, AI system, with new data, with maybe more relevant data. But then again, you don't know what exactly the properties will be. So that's really a problem, or a challenge. I should say challenge here, I guess. And it is an example for edge processing. So normally if you have sensors in the field and you have one large place where you process it, then the data is sent to that location. And here you have this large GPU cluster or something like that, and you get information out of it. It's really standard, but also really slow and dependent on large bandwidths of data connection. So what you really want to have is, again, your central point, but the processor is connected to the sensors themselves, so you get information flows instead of data flows. And please note that I, on purpose, made these arrows smaller than those, because it's really, you can really reduce a lot of data if you do that. For instance, if you have a large picture of 20 gigabyte, 20 megabyte, and you just reduce it to one thing, yes, there is a ship here, something like that. So that really helps. And if you do that, you can also use that to update someone in the field, maybe in autonomous systems, but also a soldier in the field might want to use this actual information. So if you have the edge processing, it's easier, because if you don't have these lines, it has to go like that, and then back to the soldier again. And the last part I want to talk about to you is generative AI. And it's a bit tricky because it's rather new, and I didn't do that much on it. But I also think it's really important. And again, I asked generative AI to make a nice picture of me, of this. And I think it resembles this, where you see, you have this kind of pictures with men, where you see them growing and standing in the end. I think we see a large development in AI in the last couple of years, and I want to show my vision on that. So, if you look at what's generative AI, then it's some AI that can create new content, at least based on a lot of data which is available, and so it seems that it creates new content, resembling the training data. And when I was at TNO, there was already an interesting thing from my colleague a couple of years ago, who used Van Gogh painterly, where you can say, well, you have the scene and you have the Van Gogh style, and you can separate those and then use the Van Gogh style on another painting. So these kind of things, easy to do with generative AI. And the key idea here is that they are trained on large data sets. And the most, at least for me, the most famous examples are JetGPT, GPT-3, 4, 5, 6 already, I think, almost. But also on other topics like CLIP, where you can have image processing algorithms, which I really had blood, sweat, and tears to make them myself. Now you ask JetGPT, just do that for me, or this model. And they're often based on foundation models, and foundation models are actually the models, the basic models below that, which you can retrain for a specific application. So they are pre-trained at scale. They very huge computing resources, very large data set, and they are general purpose. You can ask them anything, and then you can fine-tune them or prompt them to get your point out. And they're also multimodal. So you have, there's a lot of attention for the ChatGPT the GPT kind of things, where you talk in language, but you also have this on imaging, on audio, on planning, whatever you can think of, you can make a foundation model of, or there are foundation models of. And I try to see what I can do with it, and this is just me myself, from a Friday afternoon trying what I can do. Again, if I have this image from me at some event, and you segment anything, you get really nice segments. And imagine that 10 years ago I did this with all these hard algorithms, and now you just do that online. So this is segmentation, but you can also ask what's in the image, and you get a really nice answer back. So in this case, it said the robot features a robust, angular design with a. I was amazed that he found it was a robot, because people thought it was a lorry that we used to bring the spot robot in. But this describe anything model found it was a robot, and then find some other things in the scene. So again, amazing. And then the last one, you can also ask him to describe people. So I couldn't find it. I did it once, and it found how much the AI thought I earned. And it depended on the picture, so that was also interesting. But here it says that it's a smiling woman with shoulder-length gray hair, wearing glasses, a fair complexion, and then something about my clothes. So that's interesting. But now for the more serious part, I showed you this one. So for AI for autonomous systems, we have all these different tasks that we want to do. But if you look at generative AI, you see a trend to have that all in one model. And what you can see there is that even if you have different modules for navigation, for situation awareness, for planning, you can combine different foundation models, often via the language. So you ask something, and then the AI itself thinks, well, maybe the visual module knows something about this. He asks it to the visual model, and then it comes back to the AI, the language AI, and then you get some answers. So this is really interesting to see how all these models, all these ideas can be combined, and it results in just prompting. And to show some results that we did in the past years. And again, sometimes it's hard. We forget how easy we do things. You learn your kids to do things like opening doors, and then you try to learn the spot robot with the arm that I showed you before to open a door. And the first question is, where's the handle? Well, there are many different handles. In this case, you say we want to find the door, and we want to find the handle, and you have different handles. So we have a handle, a bar, a knob, etc. And if you know where you are, maybe you can also downscale this again. And then here we used clip to find the handles, which provided way too many things. But then we made a reasoning that the handle should be on or close to the door. So if you do that, you can actually find, in many cases, the handle. And if not, you can also say to the robot, just turn a little bit, take a different point of view, and look again. So that's one of the things which is possible at this point. And the other thing is, I talked to you about context. Here we had different context, like a living room. A living room over here, an office over here, a dining room, a train station, which are oddly close together. And then you can say, well, if it's really far away from all these things that I know on a scale in one kind of space, I can say that it's unknown. So then you have prototypes of how an office looks, how a train station looks, and then look if it's different. And the last example I want to show is on semantic segmentation. In this case, we want to have the robot drive around. And then we have different classes to do that. So it might be smooth. You can go there anyway. Rough, maybe don't drive that hard. Bumpy, please avoid. Forbidden, again, avoid. An obstacle, I wouldn't drive into an obstacle. And background, it's mainly the air. And also here you can find this classification. So here you have the output of this image. So this is all rough. We don't have many places to go here, but I wouldn't advise that in a fire. And here you see the uncertainty. So at the edges of the points you see, well, I think this is forbidden, but I'm not really sure. So you can use that as well in your manipulation. So if you do that, so you have here a better example, probably something where you might go through. You have class labels, uncertainty, and you can use that in the state estimation of your robot and your planner to finally have the fastest way and the safest way to get somewhere. To come back to the challenges for generative AI, please note that there are not so many foundation models. So sometimes you have to either use a completely different model, but it's based on the same one. And that might not be really a problem, but also all models have biases. So if there are biases in foundation models, they might have huge effect. For instance, if you asked the Dutch GPT what a woman or a man should earn, then there's a difference in there. And that's based probably on historical data. So all these models have biases, and we only have a few. So that's one. And then the other ones are mainly based on, it's hard to reproduce things. It's hard to understand why they do things. So the results are really nice. But to use it, and especially to use it in a military context, we have to know when it does something and why. So we still need to work on that to be able to use it in the real world. So that concludes my talk. What I try to tell you is I really like generative AI, and I really have the feeling that we go forward with it. But it also had a lot of challenges. And if you want to go to autonomous systems, we need to have a brain like a kid or maybe grown up to really address the robot and to make it operate safely in this open world. Thank you very much. If you have any questions.